All right, well, it's the top of the hour, but it's also very early, so we'll give another 2 minutes for people to straggle in and find your seats, sign the blue sheets, you know, things like that. The numbers are still ticking upwards steadily.
Yeah, there was some request in some other working group to have this graphed so we could know when we'd reach the median join.
When it thresholded off, right?
Yeah, exactly. I was like, actually, that's not a bad thing to have.
Roman?
I was going to say the virtual experience is replicating the real IETF Friday. It's been a long week.
Yep. Thank you for the rest of you.
Snarky comments, overheard comments from the back of the room don't always make it.
I know everybody's rushing to go to the airport and get back on the plane. You stuck around for Friday. All right, why don't we call that good? And
or have a hangover from the party the night before, which is, you know, like...
right. Or the 4 days before. Yeah.
Drinking last night, so there you go.
All right, well, welcome everybody to the Danish Authentication for Internet of Things Service Hardening, or Danish. I hope you've all had Danishes for breakfast, for those of you that are in the earlier coasts and it's not afternoon yet. I'm Wes Hardiker, and I'm here with Michael Richardson, and we are just going to turn this over in a few seconds to the real content. The mailing list is down below, and I think it's also on one of the next slides. I hope everybody is familiar with the note well. You've probably seen a bunch of these before now. We're not lawyers, so you're on your own for interpreting it, but it is important and you should follow its instructions. There's a lot of helpful information on the third slide if you want to download the slides. This is a couple of starting items. This is a non-working group forming BOF. We will still be asking some sort of working group forming BOF questions at the end, but we're not going to be discussing the charter and other things like that. That'll be done at the future. But we do want to discuss the problem space and figure out if it's in the IETF interest to take this problem space on. There are 3 drafts at the bottom. Hopefully some of you have read them. The top 2 were actually posted by the draft deadline. The third one only appeared this week. And then, of course, there's a mailing list, and you can subscribe to that as well. The first thing that we have to do is find a minute taker, and we will be here until we manage to do that. So we'd really appreciate a volunteer. My chat window disappeared. Oh. Anybody willing to take minutes today? Come on, somebody can take minutes. It's easy. We don't need extensive minutes. You know, there's a recording and everything, but at least a list of who agreed to do what and things like that would be highly helpful. I guess I will start scrolling through the list. Todd, you rock. Todd will do the minutes. We can go beyond the agenda slide. Thank you. Thank you, Todd. Appreciate it. So we'll start with a couple of things. We'll start with defining the problem space, and Ash will go over sort of what the problem is that they want to tackle. We're going to sort of go a little bit out of order because there is a presentation on sort of one future low case, which is for Loron, that we will do early. Normally we would have done that in the out of scope area at number 5, but he had a conflict, so we are going to let him go first and then do this slightly out of order. So then we're going to go into initial work areas, and that's the longest section of the presentation that'll explain sort of the proposal for going forward and, you know, what they want to tackle in sort of stage 1 of the working group. And then we'll go into some other out of scope use cases that are sort of beyond and future thinking if the working group succeeds in getting through its initial items. And at the end, we'll have an open mic where people can talk about what they think about the problem and things like that. There are clarifying Q&A points along the way. We're hoping not to do a huge amount of discussion and get through the content before we dive into real back and forth, later in open mic. And as always, we want to know, do we understand the problem? Is this problem space worth solving within the IETF? And is this a good starting set of document, and who wants to help with the effort? And that is the same thing. So with that, I will turn it over to Ash, who is going to start the presentation. I think, Ash, you said you wanted us to display the slides. Is that correct?
Yeah, if you don't mind.
Yeah, I can do that. Let me get that slide deck.
You got to turn yours off, Wes. Are you going to project it?
I was going to project it.
Go ahead. If you're ready, I'm ready too.
Oh, you can if you want.
Yeah, if you like. You just got to turn yours off if you want me to do it.
Okay.
You're doing it.
Why don't you go ahead?
Perfect. Can we skip 2 slides, please? All right. Hello. So jumping right into where we perceive the challenges to be with IoT device identity. Private PKI is everywhere. That seems to be the going theme. And establishing trust across private PKI is really challenging. This is something that's been solved in the web using the browser bundle, but we have no such, no such thing in the IoT world to help us establish trust across private PKI. There's really no good technical control to ensure that you don't have naming collisions across private PKI, even if you exchange CA certificates. So that's another challenge. The discovery mechanism by which you can, automate the process of shipping around CA certificates usually involves some sort of proprietary API operated by the certificate authority. And so all of these things kind of drive toward, getting around these challenges usually involves consolidating onto a single PKI, like an organizational PKI. But this doesn't really solve the problem. It just kind of, makes that island of trust even bigger. But very oftentimes you still need to traverse, from your island of trust to another organization's island of trust, and then you still hit the same problems. So, an example of this might be a decoupled application where devices from one application, placing telemetry in a store and forward system like a message broker. And the trust becomes implied on the message broker to honestly represent the identity of the sending system. And then, of course, if you're not attaching identity to the message itself in a decoupled system, then the identity of the sender ends up being sort of, the trust is assumed based on the integrity of the middleware. And so getting away from assumed trust, let's change slides, please.
Interrupt. Sandesh, could you turn off your videos requesting that you do, and then you typically have just one video per presenter. And then Shuman, you have your hand raised. Did you actually mean to do that?
I did not. I was just trying to insert myself into the participants like Ash, but maybe I'll do that later. So.
You are a participant, so yeah, well, you can talk when the time's right.
Okay, sounds good. Let me leave the queue.
All right.
Okay.
Thanks, Ash. Go ahead.
Okay, let's go to the next slide, please. Slide 4. So, in order to sort of alleviate these challenges, we think that a lot of this can be solved by having a broadly useful discovery mechanism for private PKI. And the features of such a system would be that it needs to work across, private PKI pretty easily. That's to, for things like enabling mutual TLS authentication between devices in the field that might belong to different PKI. It should work for asynchronous applications, object selection, the store and forward use case. It should prevent naming collisions. And it should ideally make credential rotation easier. That's another challenge that we see in the space. And then it should also work well for constrained platforms. So what we're really aiming for is to create a system of bridges between these sort of islands of trust. Next slide. So like I mentioned a moment ago, the CA bundle is really what makes WebPKI, right? That's what makes PKI work well for browsers. But WebPKI without the browser bundle would feel an awful lot like we have in IoT. And so, we can't really use WebPKI effectively for IoT. The challenges that come along with that are not the least of which are cost. So getting an agreement on roots of trust, for IoT applications, and especially when applications need to communicate with one another, like I said on the previous slide, that's cert distribution or consolidation. And then when you have multiple CAs in play, if you don't have some sort of anchoring system for the name, then you can end up with naming collisions that's, intentional or otherwise. You end up with device impersonation. And that's what drives people toward consolidation. And so let's go to the next slide. So let's look at a visual of what we think is a suboptimal information flow. On a LAN, we might have a sensor and an actuator. And the sensor is producing information that the actuator acts upon. And very oftentimes we see patterns like this, where it's a platform-based interaction. The sensor will send telemetry up to the platform will reach out to the platform, and then get the information down to the actuator. This is, next slide, please. This is a pattern we call tromboning. And this is suboptimal. You're spending what is usually more expensive bandwidth to do something that you should be doing on the local network. Next slide. And this is what we really want. There's nothing wrong with the device reaching up to its owning platform, for things like telemetry and configuration management, but we would like for information to flow from the sensor to the actuator, on the local network. This is where we end up with the challenges of getting PKI around so that you can establish trust safely between those devices. And the reason this doesn't happen more is because of the challenges with dealing with private PKI. Next slide, please. Assume trust in middleware happens, when you implicitly trust, your message broker, for instance, to honestly represent the identity of the sending entity. This is a really hard problem to solve for. Even if you have CA certificates shipped around, which are fine for establishing trust between entities, right? So the device on the left can establish a TLS session with the middleware in the middle, and each of them is confident of the identity on the other side of the connection. But the system on the right has no way of establishing a direct TLS session with the device on the left. And so while it's completely confident of the identity of the middleware, it just has to trust that the middleware is honestly representing the identity of the sender. And so next slide, please. If we want to get to a state where we can authenticate the message, then the message needs to bear a signature, as well as some indicator of the identity of the sender. And then on the recipient side, the application processing the message needs to be able to retrieve the CA certificate. This is where we usually see a proprietary API, a CA's API coming into play. So you have to tie your application. You have to have a certificate discovery process in place whereby you can go to the CA, you can grab the certificate that's used to authenticate the message. So there is some compute overhead that comes along with this on the service side. And then you also have some complexity overhead as well, because now you have to have a system that's going to manage those entity certificates, not just the CA certificates, but a certificate for every single sending entity. And this becomes even more complex when you have multiple certificate authorities in play. Then you have another API to tie off to that you use to retrieve your certificates, and it gets even more and more complex from there, trying to assign identity to the sender. In some cases, you have the certificate being sent inside the payload, but that actually for IoT can represent some significant overhead for the for the protocol itself, and IoT is very oftentimes constrained, and so you end up doing some really interesting acrobatics trying to keep your message payload size small, especially when you're including a public key or certificate in that. Next slide, please. So looking at what's already out there in the ecosystem, what we're really looking for is, do we have open standards that already exist that we can repurpose? With sort of favoring, what would represent a very easy integration path. We'd love for existing PKI to just work better, and and maybe something with a gentle adoption curve where you don't just have to flip a switch and jump up a cliff face to get to a better state. Next slide, please. So a lens through which we might examine identity systems and evaluate what might be best to go forward with. We might look at how accessible it is, which is an aspect of the entire system, right? And this is from an integration standpoint. How widely recognized is it? Might be an aspect of federation. Also has to do with the name component. So within an identity, you have three general properties, right? You have a name and a method of proving possession of the name, and then you have metadata attached to it. This conversation will center primarily around name and proof of possession. How resistant is the name to naming collision? And with PKI, this is the challenge we talk about when moving between private PKI. How resistant is it to credential theft? Compare a password to a private key. Private key you can protect with hardware. A password, is a text-based credential that's a little more challenging to protect from a physical aspect. And then the level of effort for credential rotation. That's an aspect of hygiene. And we have standards we can look to for guidance on that, but it's still a pretty big challenge with a lot of systems. Next slide, please. When we look at traditional PKI, accessibility is sort of challenging. We're oftentimes dealing with a proprietary API with the certificate authority. How widely recognized is it? And, which PKI are we talking about? The resistance to naming collisions is guaranteed only within the same certificate authority. But you can get hardware support for protecting the private key, and the level of credential rotation can be high because this is the challenge with these is the distribution of key material, after key rotation. So next slide, please. Blockchain and public key is a step in the right direction. We have standards emerging to make this more accessible from an API standpoint. W3C is very involved in that. How widely recognized is it? Well, which blockchain are we going for? How resistant is it to naming collisions? Pretty resistant within the same blockchain or distributed ledger. Resistance to credential theft carries over from PKI, and it can be hardware supported. Level of effort for credential rotation can also still be high here. Next slide, please. Using DNS and PKI is not a new idea. We do that in email, and we have other standards to support this. Using DNS as the API for PKI discovery actually works pretty well. This is something that's already in the operating system. And how widely recognized is it? I mean, there's only one DNS. You know, if you say that you have your identity in DNS, nobody asks which DNS. It's the DNS. The resistance to naming collisions is pretty good because you own your own zone. And resistance to credential theft, again, it's hardware supported. You can use hardware to protect your private key. And level of effort for credential rotation is substantially lower. And the reason for this is because once a public key is published in DNS, then it's accessible via discovery, and it's not something you don't have to distribute. It's not a distribution model where you have to copy these things out to the parties that need them. It becomes a discovery operation, and everybody's agreeing on the namespace. It makes it a lot easier to discover new certificates when they're published. Now I'm going to turn this over to Sandosh to discuss the LoRaWAN use case.
Thank you, Ash. I
For
hope
one,
you hear me. Yep.
yeah, let me interrupt for 1 second, please, which is, we did say that we would take any clarifying Q&As. Does anybody have questions for Ash before we go on to the LoRaWAN case? If so, please join the queue. All right, I think we're good. Excellent.
Okay.
Thank you. So it's actually LoRaWAN, not LoRaWAN. LoRaWAN is long-range wide area network. So
Yeah, sorry about that.
the objective for the presentation here is to demonstrate a real use case in IoT for DNS plus PKE. So that's where we have Dane. Next slide, please. So this is the basic architecture of LoRaWAN, where you have a end device. It is end device, and it is connected through LoRaWAN, that is a proprietary protocol, radio frequency, to a radio gateway, which talks both LoRaWAN as well as IP. So it receives information from the end device, and then it transfers it to IP and sends it to the backend information servers, which we call group together as backend network elements. And the connection between the radio gateway and the backend network elements are normal IP. It could be 3G, Ethernet, anything normal, as in the internet. So that's how the LoRaWAN architecture is. Next slide, please. So maybe I just would like to give just a brief intro about LoRaWAN. LoRaWAN comes under the LPWAN technology. LPWAN is low power wide area network. We have a working group in the IETF. LoRaWAN is one of the major technologies under the LPWAN category. There are a lot of use cases for LoRaWAN because it is like the internet, where you have the ecosystem. It is quite free, except the LoRaWAN technology. Anybody can be part of the LoRaWAN network. Even the networks, there are different types of networks like private, public, and community-based networks. So that's where it is interesting from the IETF perspective. So coming back, in LoRaWAN, as per the specifications, DNS infrastructure is used in two cases. One is for, we call it OTA, over-the-air activation. In the IETF terminology, it is device onboarding or bootstrapping. And for another use case, that is for roaming. So these are the two use cases where DNS infrastructure is used as per the specifications. But in normal use, there is no use. So when I say nobody is using it, it's just in the specification. And the use cases currently in LoRaWAN are using a telecom infrastructure like the hub, where everybody has to come and register to the hub to have either over-the-air activation, device onboarding when you are in a foreign network, as well as for roaming. Next slide, please. So this is the DNS hierarchy in the LoRa Alliance, the Alliance of Industries, and the institutions which develop the LoRaWAN specifications. We have two zones. One is netids.lorawan.net and another is joinuis.lorawan.net. So joinuis is focused on the over-there activation, that is device onboarding, and netids focus on roaming category. So next slide, please. So this is how the identifiers for roaming as well as for device onboarding is provisioned in the DNS. So if you could see in the left end, the join UI is IEEE UI64 identifier, which is converted to a domain name, as you could see, and it is being connected to a server. Similarly, the net ID is is a net ID where the LoRa Alliance owns that registry. So if you want to get a net ID for roaming case, you have to go to the LoRa Alliance to get this identifier. So that is used if, for example, if your device is roaming outside your network and wants to know your home network. Next slide, please. So this is how the OTA, that is over there activation flow, is done. The important part that we have here is between the NS and the DNS and the JS. So when a device is roaming or when a device comes first to a network, the network server needs to know the joint server. The joint server in IETF terminology, it is AAA server. So it needs to know the joint server to create the credentials for a secure connection. So to identify the joint server in the request that is coming from the end device, you have an identifier called join UI, and you use the join UI identifier and the DNS to find the joint server. Next slide, please. So in the roaming use case, I will not go completely because of time constraints. Similarly, if the device is roaming outside your network, so it is called the foreign network server, it has to identify using the DNS, and in the incoming packet you have the net ID. Use the net ID and resolve to the DNS zone of the net ID to identify the home network server for the device. So that is where DNS is used in LoRa case. Next slide, please. So the idea is to just give a brief introduction where DNS is used in the case of provisioning and resolution. Now we will see what is the issue. For example, if you see between the end device and the joint server for OTA, let's take the OTA case. What happens is that the root keys has to be pre-shared. So that is how it happens in LoRa Alliance as of now. So the root keys are pre-shared between the end device and the joint server. So this enables them to create a session key to establish a secure communication. Similarly, in between the end device and the application server, there is a root key called app key, which has to be pre-shared. So this is an issue because as I said in the beginning, if the ecosystem is like the internet, anybody can have a network, anybody can be the network server, anybody can be the AAA server. The issue of sharing the keys before establishing a connection is a problem. So unless and otherwise there's a proprietary network, the sharing becomes difficult. Currently, what happens is that many of them, they share the keys via mail or they print it behind the device, things like that. So that's an issue currently with the LoRaWAN setup. Next slide, please. So that is the communication between the end device and the backend network elements. Now what we see is that the communication between the backend network elements, so once the resolution is done, once you know, for example, in OTA, which is the joint server by the network server, then it has to communicate between the network server and joint server using mutual authentication. So currently, as per the LoRaWAN specifications, backend specifications, it is not normative. So the implementer could do as they want. So that's where I think it would be useful if we could have, since the resolution is done via DNS, and we could add the PKE part where we have, for example, DNSSEC plus DANE. The issue of what I say is that You don't need a certificate authority here. You can use a self-signed certificate, and the client and the server authentication, which is being developed in the Dane drafts, could be useful. Next slide, please. So here I have a resume of some other standards which are used in IoT use case, which are also using DNS. For example, here EPC is electronic product code, which is used in the supply chain industry, and the standardization organization is GS1. They use a standard called ONS, Object Naming Service, which is based on DNS. So if we see in the IoT end, if we want to have a global structure for the resolution part, DNS is needed. But what happens is that there are standards, but there is no implementation, there is no industrialization. So it is required that the standards are being developed in such a way that the resolution with the DNS plus the security part is integrated. Next slide, please. So from my perspective, from the LoRaWAN perspective, what I think is that the mutual authentication between the backend network elements is the first step to solve, because we could use it directly with the existing DNS plus PKE infrastructure. But the other case where we have to have end-to-end between the end device, which is communicating via the LoRaWAN, the radio frequency, and the IP part, is going to be difficult because there are constraints. Now is a smaller, I think a minimum packet size for a LoRa is like 52 bytes. So having a PKE certificate or a key into these 52 bytes is going to be difficult. So I know that in IETF there are other working groups working on to compress the cryptographic key so that it could be used in the IoT constraintness, but that's going to be the future end. Currently, I think for providing security mutual authentication between the backend network elements will be a use case for Danish. Thank you.
Great, awesome. So I know you have to go to a conflicting meeting. Is there anybody with questions about that? Again, that was a goal of discussing a possible future item that was not in the original list of things that we might put on a charter. Of course, that's up to the community to decide, but any questions? All right, seeing none, thanks very much. And we will then dive back into the topics related to what actually is within scope, or what we think that the initial problem spaces might be. And I think, Shuman, you're going to do that, right?
That's right. Can you hear me okay?
Yep. Go for it.
Okay, great. So let's move to the next slide. So I'll give a summary of what we expect to be the initial areas of work, or at least the protocol mechanisms that we see are the building blocks for this work if there is a successful outcome of this BOF. So we were advised by the chairs not to assume that everyone in attendance is necessarily conversant with Dane. So let me start with some very quick background. But if any of this is too basic, please yell at me, chairs, and I'll go faster. So Dane stands for DNS-based authentication of named entities and is defined in RFC 6698 and 7671. And it's a protocol that uses signed DNS records.
Can you get closer to your mic, Shuman?
Sorry?
Can you get a bit closer to your mic?
Okay, let me try that. How about now? Can you hear me better?
It's a little bit better, yeah.
Okay. All right, so I will continue. So it's a protocol that uses signed DNS records, or DNSSEC, to authenticate X509 certificates and public keys. So today, Dane is used primarily to authenticate TLS servers. There are some additional specifications listed here that define how it's employed for specific applications like SMTP transport security, and for applications that employ DNS SRV records. Next slide, please. So here's an example of a real Dane record in the wild. And this is the Proton mail service that has published a Dane record that allows you to authenticate the server certificate for the mail exchanger for that domain, the MX server. And the Dane record type itself is called TLSA, that's highlighted in red. And below the record itself is the DNS signature, the RRSIG record. SMTP transport security, by the way, is one of the areas where there has been some non-trivial adoption of Dane, at least in some areas of the internet. Next slide, please. So I'm going to quickly deconstruct the contents of a TLSA record as currently defined. And we'll use this example. The left-hand side, where the owner name is highlighted in the red box here, and it is composed of a port, a protocol, and a domain name. And basically what this says is this record pertains to the service running at TCP port 25 at the host mail.example.com. Next slide. So all the way, sorry, I think you may have skipped one slide. Can you go back? Right, yeah. So all the way at the end is the data associated with the certificate or public key for this service. And the precise nature of that data is defined by the 3 numbers that precede it. Next slide. So these 3 numbers or parameters, the first one is called the certificate usage parameter, which tells you whether the data corresponds to an end entity certificate or some issuing CA in the certificate chain that you should use as a valid trust anchor. Now, there are actually 2 classes of usage parameters. The PKIX constraining modes allow the use of DNSSEC to constrain what specific PKIX certificate or CAs you should trust. And the Dane modes are intended to use the DNS only, that is independently of PKIX. The second number is the selector parameter, and this tells you whether the data corresponds to the entire certificate or only the public key. And the third number is a matching type, and that tells you if the data is the full certificate or the full public key, or whether it's a cryptographic hash of it. And there are 2 possible hashes, defined SHA-256 and SHA-512. Next slide. So putting this example together, what this record is saying is that this is a Dane EE certificate. That's for the actual server certificate. It should be authenticated only with the DNS, and it is the SHA-256 hash of the public key in the certificate. Okay, next slide, I think. So I want to switch over to the part of Dane that is most relevant to our topic today, and that is using Dane for authenticating clients also. 2 IETF drafts we've developed address this topic. The first one specifies how to do Dane client authentication in TLS. And the second one defines a new TLS extension to convey a client's Dane identity, basically the DNS name that identifies the client. The target use cases so far envisioned are 1, IoT device authentication, and 2, authenticating clients in SMTP transport security, although you can imagine many other potential uses by other applications. The second case of SMTP, as I've already mentioned, has seen uptake of Dane on the server side. So this would be a natural complement for full mutual authentication in TLS. And I'm going to avoid the use of the term MTLS there, as if you follow the chat, you might be aware. So a point I want to make is that although this BOF is IoT focused, we would like to ensure that whatever we do with these drafts to make the IoT case work well, we still want them to be general purpose enough for adoption by other applications that may want to consider Dane for client authentication. Next slide, please. So I'll give you a quick protocol sketch. Basically, the TLS client is expected to have an identity in the form of a DNS domain name and a public-private key pair and a certificate binding the public key to the domain name. And there is a corresponding Dane TLSA record published in the DNS. On the TLS server side, what happens is the server sends a certificate request message in the TLS handshake. The client sends its certificate message and a new extension, the Dane client ID extension, which I will get to in the next slide, so bear with me a little bit. The TLS server extracts the client identity from the presented certificate or the extension, and then the server obtains the DNS TLSA record and validates it against the certificate or public key in the certificate. Next slide, please. So there is also a proposed new TLS extension for conveying a client's Dane identity. Now, generally speaking, the TLS server could find the client name in the client certificate itself. So you might be asking why we would need this. Well, it has a couple of purposes. So first, to act as a signal for support of this protocol, which can be done simply by sending an empty extension. Now, both the server and client can signal the support, but it is particularly useful for the client to do so, because that communicates to the server that it actually has a Dane record that it wishes to be authenticated with. And in environments that may support a mixture of clients, we can ensure that the TLS server attempts to perform Dane authentication only for clients that are suitably configured to make that possible. And the second reason is to convey the actual client's DNS identity in cases where it might be required. Two cases where it might be required. The first one is if you're using TLS raw public key authentication that is defined in RFC 7250. So in that case, there is no certificate at all from which the client identity can be extracted. So you need some other mechanism to convey this identity, and this TLS extension can be used to accomplish that. So, one question I actually have to the IoT system more generally is 7250 actually used anywhere in this ecosystem? To me, it's always seemed like a natural fit for constrained devices, but I don't actually have any confirmed knowledge that it is being used anywhere, but the draft makes sure that we cover that use case if necessary. So another case where this extension is useful is if the client certificate has multiple identities, and we want to tell, maybe not all of them have an associated Dane record, and we want to specifically tell the server which specific identity has the Dane record associated with it to minimize the amount of work the server has to do to perform successful authentication. Otherwise, it might try all of them, many potentially unnecessarily. I want to, did I mention this in this slide? Oh yeah, the privacy question. I also want to make a quick note about the privacy implications of this extension if it is being used to send the actual client identity. As currently specified in TLS version 1.3, this extension is intended to be carried in the certificate request and certificate messages, both of which are encrypted, so there is no privacy leakage. However, I'm assuming we'll have to support a kind of a deployed field of TLS 1.2 as well. So the TLS 1.2 version of the specification, the client has to send this in the first flight client hello extension. So this cannot be protected today without further enhancements to that version of the protocol. And you might be wondering about ECH, but as far as I've been told, that is not being defined for 1.2. So depending on the application, this privacy leakage may or may not matter to you, but we advise using TLS 1.3 if possible. Next slide, please. All right, so let's talk about the client DNS naming formats. So the TLS record format here, the RData format, to use DNS protocol terminology for client authentication, is exactly the same as specified in RFC 6698. There's no changes there. The only thing that's different is the format of the owner name, the record name format. and that has to be adapted to something more suitable to client names. The specification proposes two different formats that we think may have wide applicability, but the draft is not really prescriptive on this point. Applications could choose some other format if it makes sense to that application. So the first format is the one that we call service-specific identity. And it allows for the same client to have different credentials for different services. And it does that by encoding the application of the service name into the first label of the domain name. It also accommodates wildcards if the client uses say a common credential across many or all applications. Next slide, please. So the second format is what we're calling IoT device identity, and it proposes organizing IoT device names under a common suffix using what we're calling an identity grouping label. So that's the underscore device label that you can see in the middle of the domain name here. And this scheme permits an organization, if they wanted to delegate the management of the entire client device tree to a third party. To the left of the underscore device is the device name, which could be composed of a number of labels. And to the right is the organizational name, which may include other labels within the organization, not just the top level zone of that organization. So next slide, please. And here's just kind of an example that I just made up of what an IoT client Dane record might look like. So I'm going to skip over that because I don't think I've explained all the details already. Next slide, please. And here's a general diagram of the protocol flow, which I think I already described verbally in one of the previous slides. But basically, it involves just some relatively minor enhancements to the typical TLS client certificate authentication flow. So I've pointed out the main deltas here in red, and that is that the Dane client signals support of this extension or perhaps relays its actual identity in this new TLS client extension. And the TLS server needs to perform a lookup of the client's Dane TLSA record and validate the client's certificate and or public key against the contents of the record. And next slide, please. And just to dig into a little bit more detail, I just grabbed the TLS 1.3 handshake message diagram from the RFC, and I've annotated here with the new protocol elements in bold. So on the TLS server side, the server optionally signals support for this extension in the certificate request message. The client signals support for this extension alongside the certificate message that it sends back. And finally, the TLS server has to perform Dane authentication. And I think that covers this slide. Let's move on to the next slide, please. Okay, so as you all know, Dane authentication is dependent on DNSSEC so that you can securely authenticate the contents of the Dane records, and that is the end game we hope to achieve. However, DNSSEC is not yet universally deployed, and we'd nonetheless like to be able to use Dane or Dane-like mechanisms even before DNSSEC is fully present in the relevant pieces of the DNS infrastructure that houses the client's domain name. So we actually have an interim proposal to achieve that goal, and that involves the specification of an additional TLSA usage mode that allows the certificate data to be authenticated solely with PKIX. And we have a secondary, go ahead.
Shuman, let's pause here real quick. Brendan, did you have a clarifying question you wanted to ask? Brendan, you have your hand up. Maybe it was not intentional.
Yes. Can you hear me?
Yes, go for it.
Okay, great. So the question I have is the DNS records that we're proposing here for IoT devices. I understand that they're going to contain the Dane records, but what other information would be in that? Does it go as far as the IP address of said device?
It does not. So it is only the domain name of the IoT device. Is there a specific need you are envisioning for
No,
it
actually,
containing the IP
it's
address?
a specific anti-pattern advertising that much information about even all those device IDs under a given organization is already an attacker's dream for profiling a target. And I was just worried that you were also including specific ability to connect to said devices.
Right. No. So it includes no information about the network layer identity of the client, if that's what you're asking. So they won't be able to obtain that information from the DNS record.
Okay, great. Thanks. Go on.
Okay. All right. So let me just try to remember where I was. Okay. Yeah. So we have an interim proposal to achieve this goal of using, Dane-line mechanisms even before DNSSEC is completely deployed. And that involves the specification of an additional TLSA usage mode that allows that to happen. And there's a secondary goal of expanding the scope of Dane for IoT work to not only include sort of channel security mechanisms, but object security more generally. So there's a new draft that's recently been written to cover this, which we'll also talk about today. It's very new and certainly needs input and discussion. But I think I'm going to this was probably my last slide. I think I'm going to turn it back to Ash, who will address some of these topics and how they apply specifically to IoT.
Great. Thank you very much. Oh, Victor has his hand raised.
Yeah, Victor, go ahead. Victor, you can unmute yourself and go ahead.
Can you hear me now?
Yes, we can hear you now.
So the earlier question inspired me to make one just comment. In terms of privacy and devices being either visible or not visible, one of the things that you can do with Dane is, of course, issue certificates privately without going through any public CA. And what that helps you with is that then you're outside the scope of certificate transparency logs, which today disclose the identities of everybody who has a certificate, essentially, right? You can download the entire log and learn about every server on the internet. If a client is using Dane, then the certificate is not logged, it's generated privately. The TLSA record has the certificate fingerprint, but even the TLSA record may be hard to find unless you know its name a priori. You don't know which DNS name to query. So there's actually an advantage here that just occurred to me.
Yeah, excellent point, Victor. Yep.
Yeah, that's a good point. Let's do hold the sort of technical back and forth discussions until after the presentation. And Shuman and Ash both do note that we are running over schedule a little bit. We have plenty of time in the agenda, but to make sure that we get to Q&A, let's do speed forward.
Yep. Over to you, Ash.
All right, thank you very much. Can we skip to slide 45, please? So shifting gears, the use case that Shuman described was using Dane within the context of TLS session authentication. This is a little bit different use case for certificate discovery. And so this is using Dane records exactly as they're formatted now, adding usage type 4. And so this is to address two sort of gaps, right? So this is for entity certificate discovery, like we discussed earlier with the store and forward use case, and the challenge of integrating with private or proprietary APIs that are on a CA by CA basis. If we use DNS for certificate discovery for object use cases, this becomes a lot more straightforward of a process. And also for discovering trust anchors, which might be able to facilitate traditional TLS authentication in lieu of having DNSSEC available. So next slide, please. So we're proposing certificate usage mode 4 and calling it PKIX CD. And this is where the entity certificate, we authenticate the entity certificate using a CA certificate, which is securely discovered. The CA certificate can be, probably should be private PKI, right? And so limited or scoped to the zone that it's protecting. But the discovery of that private PKI is protected by Web PKI. Essentially, DNSSEC is a type of public key infrastructure. And if DNSSEC is not available, what we're proposing is to use Web PKI as a way of securely delivering the credentials that are, or the public keys and certificates in DNS. Next slide, please. So what this looks like is that we might have ABC, underscore device for the identity grouping label, and then vendor.example. And this would be an X509 certificate, that's stored in the DNS record. The device identifier, I think we've already covered this earlier, but the device identifier in this case is ABC, identity grouping label is underscore device, and then vendor.example is the domain name we're working with. Further breaking it down, let's get to the next slide, please. What we need to be able to do is to construct a URI where we can discover the signing certificate, right? Since we don't have DNSSEC to protect the delivery of the certificate itself like we do with the existing version of Dane. So we take the identity type, which is device. We basically, we take off the preceding underscore from the identity grouping label. We plug that into the URL. We take the organizational domain, which in this case is vendor.example, and then we construct a well-known path after that using the authority key ID from the discovered entity certificate. And so using this and requiring that HTTPS connection be protected by Web PKI, you can, of course, apply further constraints on that as to type of certificate if you really want. But we get a secure delivery method and a well-known URI whereby you can discover the certificate that's used to sign that's used to verify the entity certificate that you're retrieving using traditional DNS. Next slide, please. So using this process, we get the entity certificate from DNS at abc._device.vendor.example. We get the CA certificate from https device.vendor.example .wellknown/CA, and then the authority key ID that's taken from the entity certificate. So what's important to mention here that I didn't mention earlier is that you notice that underscore device changes when we go, we take off the underscore so that will work with Web PKI. Web PKI does not permit the use of underscores in host names. So this actually gives us a way of placing the CA certificate discovery mechanism, which is essentially, this is like content addressable storage. But that web server that's providing us this content addressable storage based on the hash of the public key is in a separate zone apart from the device certificates. And so that gives us, you can have different access controls placed on those too. We compartmentalize failure zones so that if you want to compromise the system and start presenting, false device identities, then you have to compromise both zones, or at least the web server, and start injecting bad CA certificates. So it's intended to provide a, the path to compromise this is intended to be, intentionally difficult to compromise. Next slide, please. The caveats with this, this is a little bit more complex than using traditional Dane. So you have to assure that there is name alignment between the DNS query and the contents of the certificate, right? And that's to mitigate same domain impersonation so that you don't have, so that you're not having issues with device impersonation within the same domain. cross-domain impersonation, in order to prevent that, you have to ensure that the entity name is following through with PKI presented under that domain. If you don't have a way of anchoring on the authenticating side, the relationship between the entity certificate and the CA certificate that signed it from the correct domain, then you can have cross-domain impersonation. And then, of course, you have to ensure the uniqueness of the distinguished name in the CA certificates, because sometimes, in the absence of an AKI, and this was in some testing that I did with Radius, it can get a little bit confusing depending on the implementation. So, next slide, please. So there are still a lot of, like Shuman mentioned, this is a really new draft, and there's still a lot of tons of unanswered questions. And, a couple of them are, is the DNS name, field in the certificate really the best place for establishing name alignment? Where, there's a movement, or at least an initiative to sort of deprecate the common name. Right, so is DNS name the best place to put that? Should we use other name? And the reason this is kind of coming up, we should address this early is because, there's a push with, web PKI to eliminate underscores in the DNS name, right? This isn't web PKI for the device certificates, but what are the implications for, having underscore names within, the DNS name field? And then, of course, should we be using name constraints within CA certificates and make that a requirement in the discovery process, sort of as insurance with that, that PKICs, if you're discovering, the trust chain, then you can make that an additional validation step to make sure that you're discovering a CA certificate that's bound to a very specific zone in DNS, for signing. Next slide, please. So the object security use case, has the sender's certificate discoverable in DNS. The message would contain the sender's DNS name, and then the message is protected by a signature generated using the sender's private key. And then the recipient can use the sender's DNS name to then discover the certificate, which contains a public key that can be used to authenticate the message. And then the, you can also use that to discover the signing certificate, and that can be used to validate that certificate that you discovered using DNS that doesn't have the benefit of DNSSEC. Next slide. So for a visualization of this, right? So we have messages flowing from the left to the right through, at least one middleware layer on the way to a service side that's processing this. Next slide. So the recipient extracts the name of the sending entity from the message, right? So 123._device.vendor.example, and it uses that to retrieve the certificate from DNS. Next slide. It extracts the authority key ID from the entity certificate that it just discovered. It uses that authority key ID then to build the far right portion of the URL. Next slide, please. Which looks like this. So using the device, the identity type, and the domain name, we can then construct with the authority key ID a URL where we should find exactly one PIM file with a containing the CA certificate that was used, that can be used to validate the entity certificate. Next slide. So in the process of validating entity certificates, we have also discovered a traditional PKI trust chain. Building on this, we can use that trust anchor to facilitate traditional TLS between entities, mutual authentication. And so what this kind of feeds into is a network access use case. And for this, let's kick to the next slide, please. So if we look at how this plays out, say with IETF and Radius. Next slide, please. Using Dane with pkick CD, right? So this is Dane without the benefit of DNSSEC. And then here in just a moment, I'll show how that changes for Dane for true Dane and DNSSEC for mutual TLS. But first, starting with Dane without DNSSEC. In this use case, say you have a supplier provision Dane identity, and this might be the manufacturer, this might be an implementer, or the enterprise itself, just whoever owns having that identity placed in DNS. And ideally, this will enable us to avoid supplier lock-in. The challenges for this that we're seeking to mitigate are, onboarding devices and issuing them organizational PKI identities, right? That's a manual process, and avoiding the hands-on stuff sure would be nice. Authorization gets complicated when you have multiple PKI naming conventions. That's why we oftentimes consolidate to organizational PKI, and then we want to prevent impersonation across roots of trust. And using pkick CD and IETF allows Radius to perform authorization. Beyond pkick's authentication, there becomes an authorization step of making sure that it's mapped to the right trust chain. Next slide. And sort of looking at the way it roles and responsibilities, the supplier's responsibility, the hardware supplier, is to publish a TLSA record for the device that contains a certificate with the authority key ID in it. And then they have to publish the, maintain the authority server, which contains the CA certificates, right? The implementer's responsibility is to manage the names of authorized identities in a list in the Radius server. And then the IETF server certificate, you have to get that onto the device because this is traditional PKI. There's an automation portion that happens on the Radius side to periodically update the mapping of the Dane identity to the authority key ID. But given that those certificates will not frequently rotate, this still becomes sort of a discovery process, right? Where you periodically go out and just check to make sure that the certificate hasn't been updated, and then update your mapping locally if it has. And then a periodic out-of-band CA certificate sync to enable the use of traditional TLS mutual authentication for IETF. Radius then, performs authentication using traditional PKI, and authorization happens based on the mapping of the Dane ID to whether or not the Dane ID is allowed and mapped to the authority key ID in the CA certificate that's cached in the pkick CD discovery process. This is better conveyed using an illustration. So next slide, please. So using pkick CD, the supplier places the CA certificates right in the box, that we see for web device.vendor.example. It then places the entity certificates under _device.vendor.example in DNS, and it ships those devices from the supplier to the implementer, right? Next slide. Now the implementer then configures the names of the allowed devices, the DNS names of those allowed devices in Radius. Next slide. Radius can then discover the device certificates, and it uses those device certificates to, in the process of getting those device certificates, we get the trust anchors that are used to verify those identities. So it caches the trust anchors, a reference to those trust anchors alongside the names that are placed in the Radius configuration. Next slide. So when a device attempts to authenticate to the network, then Radius then performs traditional authentication using mutual TLS. And so because it has, this trust store, that's comprised of all of the all of the appropriate CA certificates, it can do mutual TLS authentication for ETLS, and as an authorization, making sure that the certificate's issued by the right authority, then it does that authority key ID mapping, and it makes sure that the entity certificate is tied to the correct CA certificate, and then it's allowed if it is, and if it's not, then you have a cross-domain impersonation issue, and then its access is denied. But this is how it works for, if you don't have DNSSEC, then this is how you can do mutual TLS authentication for ETLS using Radius. Now, let's shift gears and look at how this plays out if you're using Dane for client identity. Next slide, please. So the desired behavior is the same. You want to avoid supplier lock-in and have your suppliers provide identities for the devices so that you don't have to operate a massive organizational PKI. Getting away from the manual onboarding of all of these devices, the challenge with authorization and different PKI naming conventions, and then preventing cross-CA impersonation, the goals are still the same. But when we use Dane for client identity and with ETLS, then Radius performs authentication and authorization based just on the list of allowed DNS names, because Dane is actually baked into the process of establishing that TLS connection. Next slide. And so this is what it begins to look like. The supplier then, if the zone is protected by DNSSEC, the supplier really just has to publish TLSA records for those devices. The implementer's responsibility is then to just maintain a list of names in Radius of authorized entities, and the server side of the Radius authentication can happen via, still it might be that manual process of installing the CA certificate onto the device itself, right? So that it can authenticate the authenticating server, the Radius server, or there's another draft that we'll discuss, maybe in more detail. It's at least referenced at the end of the presentation on the DNSSEC chain extension for TLS, which allows the delivery of a DNSSEC chain so that the record can be authenticated using Dane before you have IP connectivity. And so this allows, this could allow mutual Dane authentication in the ETLS authentication process before network access and IP connectivity are granted. And so that's still in draft state, but this presents a very interesting use case for that. And the Radius automation part, you don't need to authenticate or to automate anything on the Radius side, since this all happens in the TLS negotiation process. And then authentication and authorization, as I said, happen within the TLS negotiation. And you don't have to deal with the sort of mapping to the PKI trust anchor and all of the other stuff that comes along with that. So let's kick to the next slide, and I have a diagram to kind of walk through this. So now we just have a DNS zone, underscore device.vendor.example, where they publish device certificates. The supplier then ships the devices to the implementer. Next slide. The implementer configures names in the Radius server. And next slide. And then the mutual TLS authentication happens using Dane, just by a comparison against the DNS record in the authentication process. And so this becomes a lot more sort of straightforward of a process from the Radius server perspective once you have an updated TLS library that supports this. Next slide. And so what you get with Dane and DNSSEC is that you're able to, or really just using Dane in general, either way, you're getting manufacturer issued identity that can be reasonably used for PKI-based network access. It works with or without DNSSEC, depending on whether using PKIC CD or regular Dane for client and server authentication. PKIX-CD sort of represents the first step into Dane, and it's using WebPKI in the absence of DNSSEC. But this is sort of our this is our way of just kind of making the adoption curve for Dane a little gentler. And so using Dane for client authentication, using PKIX-CD, if you sign the zone with DNSSEC, DNSSEC actually makes things easier. And I feel like that doesn't happen very often. DNSSEC can be a little bit intimidating from an implementer standpoint, and it's really not as widely used, but this sort of incentivizes the move to DNSSEC because it actually makes stuff a little bit higher in the stack, easier and more straightforward. Next slide.
Okay. So I think Ash, unless the authors object, it's probably about time to take a discussion period and ask if there's any clarifying questions first, and then see what people think about the scope to date. We've gone through a lot of stuff, and there are some other problem spaces that can be addressed in the future, but we're through sort of the ones that are likely candidates for early targeting. Correct, Ash?
Yeah.
Okay. Hannes, go ahead.
Hey, yeah, I looked at the two documents that were mentioned initially in the earlier part of the session, which was the Dane client cert in particular, and I liked that approach, and that looked quite easy and accomplishable to me. Not so sure about then the later part. Maybe it's useful to start kind of simple and to see how that works and gain some implementation experience and then take the next steps.
Okay.
Thank you. Victor, go ahead.
I noticed that the PKIX-CD proposal has the web server over WebPKI delivering certificate chains. And it occurred to me that that's rather redundant. Once you have a secure channel to the server that's going to deliver trusted content, it suffices for it to deliver a TLSA record. If it's really a substitute for what otherwise would be DNSSEC, it can deliver just a hash of a trust anchor, and the client behaves the same way, whether it's PKIX-CD or Dane TA or PKIX-CA and so on. It delivers its chain, and the other side is responsible for securely obtaining the Dane TLSA record, either over DNSSEC or over some web mechanism that delivers exactly the same data. There's no reason to suddenly switch to PIM files on that side of the design, occurs to me. But we'll take a look at that in discussion, I guess, on our list. I just wanted to note that if I don't end up participating as much as I would hope.
Yeah. Yeah. Thanks for the feedback. I'd like to look at that.
Okay.
All right. Are there any other clarifying related questions or questions about either the problem space or this proposed solution space? Victor, you're back. Go ahead, Victor.
In the network access case, it occurs to me that the client would probably want to switch identities fairly early on in its life cycle, right? The manufacturer might sell you a device and then go out of business 90 days later or something. So while you might initially use the manufacturer-provided identity and certificate chain and so on to get the device in your network, it's probably not a good idea to expect it to be stable over the lifetime of the device. So there needs to be some kind of protocol for re-provisioning the device to a new identity provider, which is your enterprise, presumably at some point.
Mm-hmm.
rather than the manufacturer.
Sure. Yeah, you can definitely, we have protocols like Brewski to allow the migration between manufacturer issued identity and organizational identity. But we think that there may be use cases where the manufacturer issued identity might be sufficient ongoing. And so the manufacturer might even facilitate certificate rotation, using something like EST, for updating the certificate periodically and then republishing the new one in DNS. And if there's a discovery process, especially with DNSSEC and DANE, within the TLS negotiation process, that certificate can change over time, but it's still associated with the same name. So the name becomes the anchor, even though the credential may change, the credential for verifying ownership of the name may change over time. You can still pin to the name itself, and the name becomes an aspect of configuration and not necessarily even the trust chain.
Yeah, and just to follow up, I was going to mention that our protocols are designed to work sort of in conjunction with existing IoT provisioning mechanisms like Brewski and stuff, right? So they certainly plan to work with those mechanisms.
Okay, Jim? Jim, your mic's on. There we go. Go for it.
Okay. I think the scoping that's been discussed today has been fairly clear, and it looks to me to be reasonably complete. However, I think there's a bigger problem, which is that we might be talking amongst ourselves. And I think it'd be important to try and get more information and more engagement from the manufacturers and vendors of IoT devices, because let's face it, if they don't think this stuff is worth any use to them and they don't see any value in it, they're not going to deploy it or implement it or support it. And then we end up with a solution in IETF space which has got no validity in the outside world because nobody uses or cares about it. And I think we've got to be very, very careful here about the actual use of this technology. DANE is really quite hard to do because it relies on DNSSEC, which is also quite hard to do. And the point I was making in the chat earlier on about this is that we don't see a lot of uptake, quite frankly, of either DNSSEC or DANE as it is today. And that's amongst people that are reasonably clueful in terms of running sizable email installations and stuff like that. So if those kind of clueful organizations struggle to see the benefits of using DANE when there clearly are benefits, how do we think this is going to translate into an IoT ecosystem where vendors and everybody else in that space, broadly speaking, doesn't care or not care enough to do something about the problems?
That's a good point. Thanks for that. We definitely want to do this with as much industry involvement as we can bring in. The interest from the LoRaWAN side was very encouraging because it's a really strong use case. And if that community says that it needs something, we think that the sort of the breadth of that ecosystem would be very, would have sort of an elevating effect on this effort.
Yeah, I agree. But I think the problem is there will be other chunks of this IoT system that are not part of the LoRaWAN efforts. How can we reach out to them? How will they become aware of what might be happening in Danish?
That's a great point.
So Jim, I think we are doing that in the background. So I think we can talk more about that later. But I'll tell you, when I originally was working on the drafts, we were talking, this was a previous job, we were talking actively with IoT companies that were interested in deploying this stuff, right? So then there was a little kind of, that effort kind of fizzled, and then I changed jobs, but it's come up again. So I think those companies are still out there, and the plan is to reach out and re-engage them.
One of the potential selling points of this stuff, Shimon, could be the issue of software updates. How can these how can we use this technology to make it easier to do secure updates of these IoT devices, changing the firmware and such like?
Yeah.
Okay, thanks, Jim. Yeah, fortunately, deployment has gone better in the last few years and seems to be getting better and better as more major registrars and stuff are helping. But Jacques?
Hi, can you hear me?
Yes.
Good. So, Syrah, we've been working on the deployment of something similar to this. It's based on the GSMA IoT Safe standard. So we build a registry system to provision IoT devices that have eSIMs. And the good thing about eSIM, it's a crypto engine. It can create keys. And we build a system with IoT Safe so that the registry signs the keys that are created on the eSIM, and they have a unique ID. And then we use a DNS, the CERT for now. So we have CERT entries for every IoT device with a hash of the keys on the IoT device so that we can map one-to-one. So we're basically starting this process now. What we need are standard around this. So I'm late to this Danish thing, but I think it's really great to see where it's going. And I'd like to map this to making sure that the solution we're building is standard and it's secure and it meets the requirements.
So Jacques, can I read that as if this does go forward, you would likely deploy it?
Yes, but it's, the lessons learned we've done so far at the very, very beginning. For example, we tried to get MQTT provider, Solus, to change their system just to validate to do a DNSSEC query to validate the IoT device with a CERT. And that was a whole lot of work for them to take on. So just doing a CERT is simple. If we need to implement the TLSA that I've seen, it seems a little bit complex. The idea is I like the idea, but we need to make it simple.
Okay. So as far as making it simple, what do you think is the best way to get to sort of flatten the curve and to make that easier? Would helper libraries make that easier? Is the complexity around record formatting, or is it around
You got to think low-powered IoT device, which have limited bandwidth and limited crypto capabilities. So the first thing we learn is on LTE, CAT LTE, like low-powered LTE4, low bandwidth. There was not enough bandwidth to the IoT device to validate, to get all the DNS packets to go through.
Oh, right.
To do the validation. So that was the first thing we learned in the use case. So how do we simplify this? So, it starts at the IoT device with having resource limitation with DNSSEC validation. But on the other side, we did get the MTLS. I like that acronym. So the mutual TLS to work with any SIM. So we modified the IoT device to use the eSIM to do the TLS challenge identification using the CERT there, and then validate the client identity through the DNS. So maybe the way we did it is ugly and not standard. I'd like to standardize it, but there's huge value, I think, in making all of this work. So I'm in.
Great, thank you.
All right, thanks, Jacques, and I'm glad you showed up today. We were talking late last night. All right, I see nobody else in the queue. So I'd like to ask sort of the following question for comments, if anybody wants to join the queue to answer it, which is, is the problem space understandable? Based on the discussion in Jabber, which I think Michael's been following better than I, and based on the comments at the microphone, it seems like the problem space has been well defined and everybody understands it. If you disagree with that and you're confused, do let us know. And so the next question then is, is the problem space worth solving within the IETF? It seems like there is general support for that. And I'd like to hear if anybody, thinks that this isn't something that the IETF should take on in general. And as long as nobody's joining for that, we'll also say, of the 3 starting documents, there are 3. I don't know how many people have read the third one because it appeared on Monday, which was beyond the normal mandatory must-read documents to participate in the discussion. Does it seem like those 3 documents are a good direction or a good place to start? I will pause for Q people.
A question. You said 3 documents. Which are the 3? I remember the first 2, and then which one was the third?
I had that somewhere. These 3. So the PKIC CD is the third one, and that's the one where there was more discussion in the Jabber room, I think, about whether that approach was. I think it might have been you, actually, Hans, that said that the first 2 were likely a good starting place, and the third one, the PKIC CD idea, maybe should be tabled for future charter items.
Well, it wasn't on the last one. There was a lot of discussion, which wasn't just me talking to myself.
Yes, yeah. So thoughts on is this an acceptable starting place for the IETF to focus on, with especially the first 2 drafts as possible charter items to consider once we get to the point of writing the charter. Again, this is a non-working group forming BOF at this point.
Yeah, so Wes, I would suggest the third one, just keep it there tentatively because it just came out this week, so probably not a lot of people have had time to read and digest it.
Got it. Looks like there's more dialogue going on in the chat that seems to back that up. So that's good starting points. Thank you. Jim, go ahead.
So I've just got a question on next steps. Will the intention be to have a working group forming BOF at IETF 111, or would you prefer to see more discussion on the list and then make a mind about that later? I'd like to know where this stuff is headed.
That is a very good question for our AD, Roman.
Hi. So this is Roman. I mean, that's a great kind of process question. It all really depends. If we are at the point where we feel like we understand the problem, we have concurrence that this is something we want to solve, and we have a reasonable agreement on part of the starting point, it seems like the next step would be to polish a charter. If we can polish that charter to the point that there is agreement across this community of discussion, we could directly go to trying to form a working group without having another BOF. If we think that the conversation around the chartering and the scope would require a BOF, we could absolutely do that. So we have the option for both. We've done it both ways in security.
Thanks for the answer, Roman. Hannes?
Sorry, if I could just jump in and add a little bit, Roman. We definitely do not want to wait to have the discussion to have a second BOF. We should definitely continue to have the discussion. And I think, Roman, your comments were predicated on the fact that we have the discussion to understand what we do or do not agree on.
Yeah, I mean, absolutely. We should not do a halting function. The next time we talk is the next IETF meeting. We should, roll this into the mailing list. We should, if that it looks like where we're heading is we want to talk about charter, we should start dropping some charter on the mailing list and iterate through it and, shoot for not even needing a new BOF then if there's that much interest.
Great.
One of the key ingredients to get us across that finish line, I will say, beyond making sure we understand the task, is having a conversation about question number 4, which I think Wes is going to lead us to shortly, which is who exactly is going to kind of work on this, and do we have a sense for who'd be willing to take it, who'd be willing to kind of review, edit, implement, etc.
Exactly where we're headed next.
Ask a question?
Yeah, so Hannes, go ahead. But anybody that wants to participate as we're doing Q&A, please do feel free while you're talking and posing your question or discussion item. Feel free if you're interested in helping us at the same time.
I was wondering whether there's room for an architecture document in the group as well. Like the two documents are more like really the protocol specifications, the first two, and the reason is because there obviously is some architectural aspects here in this work. And in my experience from the SU Deep RADS groups, the architecture documents have been extremely helpful in understanding how the different pieces fit together and identifying like who actually needs to be involved in making work successful.
Yeah, so this is Shumon. So Hannes, thanks for that comment. I think that's a great idea. I've actually thought of the same thing myself, but thanks for proposing it. I mean, if the participants think that would be a useful document to add to this basket of work, I think we would be willing to take it on and receive help from you or anyone else who would like to help us flesh out that document.
Raman, you're in the queue.
I wanted to endorse Hannes's proposal. I think based on the conversation we saw in Jabber, where it seemed like there was a lot of discussion about how this domain is different than another domain and all the clarifications we needed to have. I think that kind of preamble of having an architecture document kind of scoping the insertion of the scope that appears to be in those two documents would be exceedingly helpful.
Yep, great. Thank you, Robert.
Right. I see no more participants in the queue. If people are, wanting to help, of course, signing up to the mailing list is the first step to do that, as well as reaching out to the authors and reading the documents and complaining wildly on the mailing list or giving wild advocate support. Why don't we shift now into, since there's still nobody in the queue, why don't we shift now into the other problem spaces that could be potentially addressed in the future. Again, these are slides that will be discussing things that are likely out of scope for the beginning, but just to see other areas where this sort of technology might help. Does that work for you guys? So Michael, that leaves you. Can you go back to presenting the slides? Thank you.
All right, so let's walk through a thought experiment of how multicast DNS and Dane might work together. Next slide, please. So let's just say that there is a taxi service, and in order to remain compliant with their insurance company, they have to retain a certain number of days of forward-looking dash cam records, and so the constraints involved in implementing such a thing is that if this is on the order of months, then it might be very expensive to put that kind of storage in every single car. The cost of cellular bandwidth to backhaul this to a cloud storage solution might be pretty tremendous, especially depending on the quality of the video. And then local storage, would be the least expensive way to do this at the say at the garage or at the central office. So as a solution, maybe we want to have the vehicles only have to retain about a day's worth of video, right? And so when they pull back into the station at night, then these would flush up to, the storage system in the, at the garage. And so using office Wi-Fi for that gets around bandwidth problems, and having video, these video files with a signature, from the dash cam's private key also gives you some assurance that it hasn't been altered. And so let's look at how Danish might play into such an application. Next slide. So let's say that we have vendor.example is the domain that owns the identity for the DVR system or video storage system at the garage. And then you have another vendor that produces dash cams for taxis, and that's taxi.example. You have a DNS record for the DVR system, and the DVR system has a local IP that's advertised, taking the leftmost label from the DVR's DNS name. Then we have an advertised IP address as well as HTTPS service advertised on multicast DNS. And then car54, has, the dash cam identified by car54 _ auto.taxi.example has a TLSA record in DNS. And so the first step is when the car gets back to the garage, then maybe it connects to the network using EAT-TLS in a way that we described earlier in the conversation, which might be Dane enabled. And so the next step, next slide, please. The car knows beforehand the DNS name of the DVR device, right? Which is where the TLSA record can be discovered. So breaking that identity apart, we can take the leftmost label and we get the MDNS instance name. And so the MDNS service query becomes, we're looking for HTTPS services on the local network for recorder 56. We can use that to, get the local IP and port, and so now, next step, or next slide, please. Then we can begin a TLS handshake, right? So we have the IP and the port discovered via multicast DNS, and then we have the proper DNS name that's taken from the, what the car knew beforehand as far as, this is where the identity is in the DNS, where the TLSA record resides. And so the car then begins a TLS negotiation with the DVR system saying, okay, my Dane client ID is car54 _auto.taxi.example. And that's, and then the DNS name of the, recorder 56 _DVR.vendor.example is used in the SNI for establishing that in the TLS handshake. Next slide. And so the server certificate is then matched against the DNS record for the Dane DNS, the TLSA record rather, for port 443, TCP recorder 56 _DVR.vendor.example. This follows the pattern for the existing Dane standard for server authentication, right? And so this is already sort of codified. Next step, next slide. And then the car's dash cam presents a client certificate to the server. Next slide. And then the server then verifies the certificate that's presented against the record in DNS for car54 _auto.taxi.example. And that's how we complete the mutual TLS authentication with the DVR system on site. Next slide. And then we can upload the signed dashcam footage to the DVR system. We have identity attached to the object that's being uploaded via the signature, and of course you would probably include the name of the signing entity in that as well. And all of this happens, and if we think about the way that trust would be described in this application, then for network access, you would have the name of the dash cam, as this is an allowed entity for the network, for establishing trust between, and allowing authentication authorization between the dash cam and the DVR system. The DVR system needs to know the names of the allowed entities that are allowed to authenticate and to upload videos, and the dash cam only needs to know the DNS name of where the TLSA record resides of the sorry, lots of words, lots of coffee, of the DVR system in DNS. And so beginning with those two DNS names, we can then compose the multicast DNS queries for locating those resources locally and then performing authentication. And so, yeah, so that's, and these are probably the newest slides in the whole deck. So we can definitely take questions on how this use case might work.
Great. Any questions on this potential future item not likely to be chartered this time out? Nope. All right. You want to go on to the next one?
Cool. Yeah.
Great.
So let's bump 2 slides. Scope of work. The core objectives are are sort of getting these 3 drafts established. And so the first 2 are those are the 2015 drafts for the TLS negotiation using Dane and DNSSEC. And the third one is Dane without DNSSEC using the using a WebPKI. The peripheral objectives beyond this, but still sort of within scope. Next slide, please. Is that in order to get adoption on the server side, it would be very, very useful, we think, to have this supported by standardized proxy headers for HTTP and lower level TCP proxies. So getting, as well as the email ecosystem already uses Dane, and this would be a great place to go ahead and use Dane for client identity. But this involves, seeing how this plays into Start TLS. And then, of course, the object security use case for Hosey and Cozy, updating the X509 field usage to cover that.
So, Michael, I assume you're in the queue without a hat. Is that correct?
That's a good question. So when you say HTTP, you're talking about like Brian Campbell's. This is for document that didn't go anywhere on carrying the client certificate in across the framework. Is that what you're talking about?
This is a little bit. This is like that, but a little bit different. The way I
Okay.
sort of envision this happening is just the client name, just the
Right.
Dane. Yeah, just carrying the name. We don't have to carry the certificate into the application because you're really just authorizing a name. So it would be a different header value than that. This is, specifically a new header value. I think let's kick to the next slide. I have a little bit more details on HTTP and proxy protocol headers and how those might play out. So this would establish a new header field called, X forwarded Dane client ID. And this would basically take it out of the client hello, or however the identity is conveyed within the TLS session establishment for the Dane client identity, and then forwarding that up into the application as a, or through the middleware layer to the application server as an HTTP header. And then for the TCP proxies and load balancers, we would look at something like the proxy protocol, which is, I don't think that's maintained inside IETF. That's maintained, I think, by HA proxy. Could be wrong. Yeah, so this would be implementing a new header TLV for that, which would convey the Dane DNS name that the identity was authenticated against. That's sort of how I think this could play out. Of course, this is definitely open to discussion about the best way to accomplish this. But I think that if we get this into something that's consumable by load balancers, it would make it easier for, that's sort of the a narrower space to implement in and get the most benefit. So then you don't have to worry about implementing it for every single, HTTP server, because very oftentimes you'll have an HTTP server behind a proxy of some sort, and having the proxy do the authentication and then just pass a header in that an application on the other side can easily process, we think would make things much easier for adoption. So that's sort of our thoughts on protocol headers. Did that answer your question?
Got it.
So I think he said.
Do you mind if I ask a question on the dash cam example? I'm a little slow. understanding this. What are the assumptions that you make on the dash cam example? Is it the car is configured to know what the recorder in the home is? And also, since you use EAP TLS, initially you obviously have configured it to use a specific network at home. Is that correct?
Correct. So that would be part of the onboarding process for the dash cam into the taxi company's organization. Is the dash cam would have to be configured, for the EAP TLS, whatever that requires. If it's using, Dane, and I think the ideal situation is where we would have, the trust, DNSSEC and the trust chain conveyed via the TLS extension for DNSSEC. But there is definitely, an onboarding process whereby you have to configure the dash cam to attach to the network, and then you have to configure the dash cam with the name of the DVR system, the DVR system's DNS name.
Okay.
So this does assume that there is some configuration of DNS names who are allowed to access the network and allowed to access the DVR.
Okay. Thanks.
Yeah.
That would help. Yeah. The clarification.
And for what it's worth, hope the hope is that the configuration of trust in an application like this could look. So my my history, professional history, was I used to do NetOps, and so describing things in the terms of a network access control list is something that works pretty well for the eyes. And so what we're kind of going for is that from an operator standpoint, it would be really nice if we can get this, if we can make the protocol as straightforward as possible. And if you can configure network access via, these are a list of allowed entities that are really not hard to look at, just simple DNS names. And so being able to describe communication patterns in lists of DNS names, we think would be, make adoption even easier. For small shops, and of course, mega scale stuff, you would have automation for, but that's sort of the ease of adoption we think could be affected by just, having sort of a simplified approach to describing trust like that.
Okay.
All right, so we probably have 3 minutes before we're going to cut into final questions for the BOF, since there's about 7 minutes left of the presentation. Is there any other topics that you guys definitely want to hit, so we make sure you get those on the table? I'm giving you the opportunity to skip around if you like.
Okay. Yeah, because we definitely have a handful of slides. So the Shimon, do you have anything you want to cover? I have a couple of things, but if you want to jump in.
No, I'm good. Go ahead.
Okay, cool. So really quickly, there are a couple of adjustments to Jose and Cozy. And if we look at slides 84 real quick, these are really just sort of defining new URIs that are valid for, for specific fields that already exist in these standards. And then Cozy might be even easier. Next slide, please. Because really we just need to support the application DNS media type. So eligible for inclusion, let's run through these really quick. SMIME is a standard which exists. Next slide, please. 2 slides. SMIME is a discovery mechanism for SMIME certificates that's based on Dane, and this exists as an experimental standard. It's already out there. This would be easier to adopt for folks who don't have DNSSEC using something like pkix-cd. And so updating this, would really, this fits with the pattern that we've already established for pkix-cd. Identity naming, DNS name, label construction, things like that fits really easily here. We think this would be a quick hit if anybody's really interested in picking it up. The next slide, please. The DNSSEC chain extension for TLS, we think would be a really big win because then that would further reduce the onboarding time for devices. This allows the allows us to convey a trust chain without, for DNSSEC without IP connectivity. And this is sort of the ETLS use case. There might also be an option for making SIP authentication easier via the next. Oh, Victor, you want to jump in real quick on this?
You go ahead, Victor.
So for PKXCD, I don't even think we need a new DANE usage for it, frankly, because the signaling that you want to go out of band and not rely on DNSSEC optionally can happen via the new HTTPS records that are being introduced in DNSOP that hint at, this session should be, trust building should employ, the well-known URI mechanism. Some keyword in HTTPS record can signal that. And then when you contact the server, you get a regular DANE record, but the securing the channel against tampering is done via WebPKI. So I don't think it even is necessary or makes sense to have a new DANE usage for this. HTTPS can carry lots of information, and this can just be one of the pieces of information in the HTTPS record that the client retrieves before it builds the TLS connection.
I like it. Simpler is better.
Okay, cool. So we are pretty much out of time. Why don't you go through the last 3 topic slides real quick and just say the titles without describing them? Yeah,
sure.
So,
DANE for SIP authentication, we think is another opportunity. Updating OAuth 2 for mutual TLS using DANE could be an enabling thing as well. And then MLS, message layer security, might benefit from using DNS as a directory for public keys. And in the appendix, we've got a list of some of the adjacent standards and drafts that we discussed throughout the topic today. So
yeah, I must say that appendix is just awesomely well put together. So all of these slides are available for downloading from the data tracker. So I encourage everybody to do that so that you can take a look at the full presentation. We actually did get pretty much all the way through it. Are there any, I think that we're fairly well understood in this point. I think that we've sort of answered all the questions from the BOF point of view. Roman or Ben, I guess I should give either one of you an opportunity to ask any final questions you want to know about.
No, I have no more kind of questions. I mean, I would really just say due to the preparation of the proponents, and thank you kind of to the chairs, we've actually got we have a scope here, we have an understanding of the problem, and it looks like the next steps are to return to the mailing list and really just hammer on the specifics of how much scope we want to talk about. And to reiterate the previous conversation, that let's not wait for an in-person meeting, and if we can, continue to discuss productively on the mailing list, we can get to the point on an agreed upon charter. The key thing I would ask the folks discussing on the mailing list is that we get a better sense of who we'd like to work on this, as that will be another key ingredient in addition to scope to allow this to progress forward. But thank you for all the work that went into this, and thank you to the community for all their helpful feedback, both here and the very active Jabber channel.
Yeah, and thank you to the ADs and the proponents for putting this together in such a well organized mechanism. Michael, anything else you want to add?
Nope, I just thought I'd show my face again.
Good plan. All right. All right. So I think that we will call it here. We have like a minute left, and I encourage again everybody. Successful working groups come out of an active mailing list. So if you want to participate and want to help out, certainly joining the Danish mailing list is the best way forward at this point. Thanks everybody for coming, and please enjoy the cookies in the Jabbertown. Jabbertown. I like that. We should call it Jabbertown. How come we didn't call it Jabbertown?
Jabbertown. Yeah, we probably could. Probably available. All right. Thank you.
All right. Thanks all.
Thanks.